Technically, Docker is one implementation of the container-based virtualization technologies. Let's take a look at how virtualization technology has evolved over time. In the pre-virtualization days, we're using big server racks. Underneath, we have the physical server. We install the desired operating system on it. Then we run the application on top of the operating system. And each physical machine would only run one application. So what was the problem with this model? First of all, we have to purchase a physical machine in order to deploy each application. And those commercial servers can be very expensive. And we might end up only using a fraction of the CPU or a memory of the machine. The rest of the resources are simply wasted, but you have to pay for the whole hardware upfront. Secondly, deployment time is often slow. The process of purchasing and configuring new physical servers can take ages, especially for big organizations. Thirdly, it will be painful to migrate our applications to servers from different vendors. Let's say we install our application on an IBM server. It would take us lots of effort to migrate to Dell servers. A significant amount of configuration change and manual intervention is required. The rescue is the Hypervisor-based virtualization technology. Let's take a look at this virtualization model. Underneath, we have the physical server. Then we install the desired operating system. On top of the operating system, a hypervisor layer is introduced, which allows us to install multiple virtual machines on a single physical machine. Each VM can have a different operating system.
For example, we can have Ubuntu installed on one VM and Debian on another.
In this way, we can run multiple operating systems on a single physical machine, and each operating system can run a different application. This is the traditional model of virtualization, which is being referenced as the hypervisor-based virtualization. Some of the popular hypervisor providers are VMware and VirtualBox. In the early stage, users would deploy VMs on their own physical servers. But nowadays, more and more companies have been shifted to deploy VMs in the cloud with providers such as AWS and Microsoft Azure, which means we don't even have to purchase physical machines upfront. There are some huge benefits with this model. First of all, it is more cost-effective. Each physical machine is divided into multiple VMs, and each one only uses its own CPU, memory, and storage resources. We pay only for the compute power, storage, and other resources you use, with no upfront commitments, which is a typical pay-as-you-go model. Secondly, it's easy to scale. With VMs deployed in the cloud environment, if we wanted more instances of our application, we don't need to go through the long process of ordering and configuring new physical servers. We can simply click the mouse and deploy more VMs in the cloud. The time taken to scale our application can be reduced from weeks to just minutes. This results in a dramatic increase in agility for the organization. This hypervisor-based virtualization model has obvious advantage over the one application on one server model, but it still has some limitations. First of all, each virtual machine still needs to have an operating system installed. This is an entire guest operating system with its own memory management, device drivers, daemons, etc. When we're talking about a Linux operating system, we're talking about a kernel.
For example, here we have 3 host operating systems and 3 kernels.
Even though they can be 3 different kernels, we're still replicating a lot of the core functionality of Linux. In this traditional hypervisor-based virtualization model, we have to have an entire operating system there simply to run our application, which is still not inefficient. Secondly, application probability is not guaranteed. Even though some progress has been achieved in getting virtual machines to run across different types of hypervisors, there is still a lot of work to be done there. VM portability is still at an early stage. Finally, the container-based virtualization technology comes out. Docker is one implementation of the container-based virtualization technologies. Let's take a look at the diagram here. Underneath, we have our server. And this can be either a physical machine or a virtual machine. Then we install our operating system on the server. On top of the OS, we install a container engine, which allows us to run multiple guest instances. Each guest instance is called a container. Within each container, we install the application and all the libraries that application depends on. The key to understand the difference between the hypervisor-based virtualization model and the container-based virtualization model is the replication of the kernels. In the traditional model, each application is running in its own copy of the kernel, and the virtualization happens at the hardware level. In the new model, we have only one kernel, which will supply different binaries and runtime to the applications running in isolated containers. So the container will share the base runtime kernel, which is the container engine. For the new model, the virtualization happens at the operating system level. Containers share the host's OS, so this is much more efficient and lightweighted. You might want to ask, what do we gain by running those applications in different containers? Why can't we just run all applications in a single VM? This comes through the nature of isolation. As you know, most applications depend on various third-party libraries. Let's say we want to run 2 Java replications with 2 different JREs. This is going to be quite challenging if you want to run those 2 applications in the same VM without introducing any conflicts. By leveraging containers, we can easily isolate the 2 runtime environments. Let's say application A requires JRE 8. Then we just install JRE 8 in the first container and run application A in the first container. For container B, it requires JRE 7. Then we just install JRE 7 only for second container and run application B inside the second container. In this way, we have 2 containers on the same machine running 2 different applications, each with a different JRE version. This is what we call runtime isolation. Comparing to hypervisor-based virtualization, container-based virtualization has some obvious benefits. Firstly, it's more cost-effective. Container-based virtualization does not create an entire virtual operating system. Instead, only the required components are packed up inside the container with the application.
Containers consume less CPU, RAM, and storage space than VMs.
That means we can have more containers running on one physical machine than VMs. Secondly, faster deployment speed. Containers house the minimal requirements for running the application, which can speed up as fast as a process. A container can be several times faster to boost than a VM. Thirdly, great portability. Because containers are essentially independent self-sufficient application bundles, they can be run across machines without compatibility issues.
That's it for this lecture. I'll see you later.
Let's talk a little bit about Docker's client and server architecture. Docker uses a client-server architecture with the daemon being the server. The user does not directly interact with the daemon, but instead through the Docker client. The Docker client is the primary user interface to Docker. It accepts commands from the user and communicates back and forth with the Docker daemon. There are 2 types of Docker clients: the typical command line client and Kidmatic, which is a Docker client with graphical interface. So if you don't like working with commands, Kidmatic is something you should check out. The daemon is the persistent process which does the heavy lifting of building, running, and distributing your Docker containers. Docker daemon is often referred as Docker engine or Docker server. On a typical Linux installation, the Docker client, the Docker daemon, and any containers run on the same host. You can also connect a Docker client to a remote Docker daemon. We will cover more about this later. But you can't run Docker natively in OS X or Windows, because Docker daemon uses Linux-specific kernel features. So on OS X or Windows installation, the Docker daemon is running inside a Docker machine. The Docker machine is a lightweight Linux VM made specially to run the Docker daemon on OS X or Windows. Let's get started on installing Docker on our local machine.
This lecture applies to you if you're using Linux or you are using Mac and your Mac version is OS X 10.10.3 or newer, or you're using Windows and your Windows version is Windows 10 or newer. Otherwise, you can skip this lecture and follow the instruction of the next lecture to install Docker Toolbox on your local machine.
Here we Google Docker install. The first entry is Docker's official installation page. Just click the link to enter the installation page. The steps required to install Docker vary depending on the operating system you use.
If you're using Linux, you can just follow the corresponding installation instruction on this page to install Docker on your operating system.
Since Docker is a technology built around Linux containers, people developing on non-Linux platforms would need to use some forms of virtualization to run Docker. If you're running Windows, just scroll down and click the Windows installation link. As you see, there are two options for installing Docker on Windows: Docker for Windows and Docker Toolbox. Now, if you have Windows 10 or a newer version installed, you will be able to install Docker for Windows. Docker for Windows runs as a native Windows application, and it has a built-in virtual machine inside the app, which saves you tons of efforts from managing the VM by yourself. Docker for Windows is the desired way to run Docker on Windows machine, as long as you meet minimum requirement. You can just click the Getting Started with Docker for Windows link to start the installation. Since I'm using Mac, I'll be demoing how to install Docker for Mac on my Mac machine. But the steps should be very similar between Windows and Mac. Here, I scroll down and click the Mac installation page. Similar to Windows, you also have two options here. You can either install Docker for Mac or Docker Toolbox. If your Mac is 2010 or a newer model, and the Mac version is OS X 10.10.3 Yosemite or newer, it is recommended to install Docker for Mac, which runs as a native Mac application. I'm running a relatively newer version of Mac. Here, I just click Getting Started with Docker for Mac.
Let's download the stable version. As you see, it is downloaded the installer.
I'm fast-forwarding the video until the download is complete.
Now the installer is downloaded. Let's click it.
Then drag the whale to the Applications folder. Just type your password to proceed. Then open the Applications folder and double-click the whale icon. Click Next. Now installer is asking for privileged access, as it needs to install its network components. Just click OK and type password to proceed.
Docker has been installed on my local box.
As you see, we have a whale icon on the menu bar on top of our desktop. This initialization phase might take a while to complete. I'm fast-forwarding the video until it's finished. This is what you would see if everything goes well. Now Docker is starting. Finally, we got Docker up running. Let's open a command line terminal. Then type Docker info. Docker info would display the system-wide information about Docker. As you see, Docker is running inside a Linux virtual machine. You can also configure your Docker preference by clicking the whale on the top menu bar, then select Preferences. Now we're under the General tab. Docker for Mac is set to automatically start when you log in. We'll leave this option checked so that we can have Docker automatically start when we log in into our desktop. You can also configure the number of CPU processors. You can increase processing power for the app by setting this to a higher number, or lower it to have Docker for Mac use fewer computing resources. By default, Docker for Mac is set to use 2 GB runtime memory, allocated from the total available memory on your Mac. You can increase the RAM on the app to get faster performance by setting this number higher. That's it for this lecture. I hope you've enjoyed it. In this lecture, we'll see how to install Docker Toolbox on your local box.
This lecture applies to you if you're using Mac and your Mac version is older than OS 10, 10.10.3, or you're using Windows and your Windows version is older than Windows 10, or you want to install Docker Machine or Kitematic instead of Docker Engine. Otherwise, you can skip this lecture and follow the installation guide of the previous lecture. Here, we Google Docker install. The first entry is Docker's official installation page. Just click the link to enter the installation page. The steps required to install Docker vary depending on the operating system you use. If you're using Linux, you can just follow the corresponding installation instruction on this page to install Docker on your operating system. Since Docker is a technology built around Linux containers, people developing on non-Linux platforms will need to use some forms of virtualization to run Docker. If you're using Windows, just scroll down and click the Windows installation link. Then click Docker Toolbox. Then you can click Get Docker Toolbox to download Docker Toolbox installer for Windows. Since I'm using Mac, I'll be demoing how to install Docker Toolbox on my Mac machine. But the installation steps should be very similar between Windows and Mac. Here, we click the Mac OS X link to go to the installation guide for Mac. Then click Docker Toolbox. As you see, we'll be installing Docker Toolbox, which will install all the components you need to run Docker on Mac OS. Just be aware that you need OS X 10.8 Mountain Lion or newer version to install Docker Toolbox. Here, we click Get Docker Toolbox link. Then download the installer for Mac. The download is going to take a while. I'm fast forwarding the video until the download is complete. Now the installer has been downloaded. Docker Toolbox includes a minimum boot to Docker virtual machine, which will run inside VirtualBox. If you have VirtualBox running, make sure to shut it down before running the installer to avoid conflict. Let's double-click the icon to run the installer and accept all the default. The installer is going to install Docker Client, Docker Machine, Docker Compose, Kitematic, and Quick Start Terminal app. Docker Machine is a tool that lets you install Docker Engine on virtual hosts and manage the hosts with Docker Machine commands. Docker Compose is a tool for defining and running multi-container Docker applications. Kitematic is graphical Docker client. If you don't know what they are, don't worry. We'll talk about them in more details later. Type in the password to proceed. Now the installation is complete. Here we choose to start with the Docker Quick Start terminal. Now it is provisioning the Docker machine. The first time you run it, it will take a while. We'll just fast forward the video while the machine boots up. This is what it looks like if everything works successfully. This terminal is effectively a Docker client which takes the user input and send them to the Docker daemon. Here we can run Docker machine ls command, which will last all the Docker virtual machines. As you see, we have our default Docker machines up. The Docker daemon is running inside the Docker machine. If you run Docker version command, it will print the version for both client and Docker server. Docker server refers to the Docker daemon. Here, if you launch the VirtualBox, you'll find out the installer has installed and configured a boot Docker VM, and the Docker daemon is running inside the VM. Before we finish this lecture, let me show you how to run Docker next time. Once you have the Docker Toolbox installed, you can access Docker anytime by opening the Docker Quick Start terminal again. See? We get back our Docker client. There are several important concepts we must understand before we start playing with Docker. The first two concepts are containers and images. Images are read-only template used to create containers. Images are created with the Docker build command, either by us or by other Docker users. Because images can become quite large, images are designed to be composed of layers of other images, allowing a minimal amount of data to be sent.
when transferring images over the network. Images are stored in a Docker registry, such as Docker Hub. We'll talk about it in a minute. Next, we'll talk about containers. To use a programming metaphor, if an image is a class, then a container is an instance of a class, a runtime object. Containers are hopefully why you are using Docker. They're lightweight and portable encapsulations of an environment in which to run applications. We create a container from an image and then run the container. And inside that container, we have all the binaries and dependencies we need to run our application. Here are another two important concepts about Docker: registry and repositories. A registry is where we store our images. You can host your own registry, and you can use Docker's public registry, which is called Docker Hub. Inside a registry, images are stored in repositories. Docker repository is a collection of different Docker images with the same name that have different tags. Each tag usually represents a different version of the image. Let's take a look at the Docker Hub. Docker Hub is a public registry which contains a large number of images you can use. Here we Google Docker Hub. The second entry is what we are looking for. Just click the link. Here we click Browse to see what we can find. As we see, there are some popular official repositories listed here, such as Nginx, Ubuntu, and Redis. Official repositories are certified repositories by Docker. For each repository, we can also see the number of stars and pulls, which indicate the popularity of each repository. You can also search other repositories here. Let's say we want to find some MySQL images. Let's type MySQL and hit enter to search. See? So Docker Hub found some MySQL repositories here. Note the first one is marked as official. New Docker users are encouraged to use the official repositories in their projects. These repositories have clear documentation, promote best practices, and are designed for the most common use cases. Docker Incorporation, which is the company behind Docker, sponsors a dedicated team that is responsible for reviewing and publishing all official repositories' content. It is also ensured that security updates are applied in a timely manner for official images. So when we get started with Docker, try to use official images so that we can get the most support from the community. All the other repositories are also MySQL repositories, which presumably contains MySQL images. They are contributed by other users in the community. So how can we tell which one is an official image and which is not? First of all, as we mentioned before, official images usually come with an official mark. Also, the name of an unofficial image usually has a namespace before the actual image name, which is often the username of the user who created the repository. Here, let's click the link of the official MySQL repository. We can see the information about this repo and clear documents about how to use this image. If I scroll up and click the Tags tab, we can see the repository has several tags. In most of the cases, the tag means the version of the application or tool in this image. So an image is specified by its repository name and tag. Even the same image might have multiple tags. If you don't specify a tag, Docker will use the default tag, which is latest. We'll get into more details about this when we start playing Docker run command in the next lecture. In this lecture, we'll learn how to create and run our first container. We're going to create a container from an image. The image we're going to use here is called BusyBox. Let's go check it out. Here, we're at Docker Hub website. Just search for BusyBox. Let's click the first one, which is the official BusyBox repository. We quickly scroll down the document. As you see, BusyBox is a tiny image, which is only about 1 megabyte. This is the main reason we choose BusyBox. because of its tiny size, so it would take little time to download. Let's check out the Tags tab. BusyBox has various different tags. Here, we pick tag 1.24 to run our container. Let's close the browser and open the Docker Quick Start terminal.
If you have installed Docker for Mac, Docker for Windows, or you are using Linux, you can just open up a normal terminal.
When we use the image to create a container, Docker will first look through our local box to find the image. If Docker is able to find the image locally, it will use the local image to create the container. If Docker can't find the local copy of the image, it will download from remote registry. To find out what image you have in your local box, we can run the Docker images command. See, we don't have any images in my local box. Now let's start running our container. To run a container, we will use docker run command. Docker run command will create the container using the image we specify in the command line, and it will spin up the container and run it. As we talked about in the previous lecture, an image is specified by the repository name and tag. We need to put a column between the repository name and the tag. So let's use BusyBox image with tag 1.24. After that, we need to specify what command we would like to run in that container and pass the argument for that command. The command we're going to run is echo, and let's put the argument hello world. So the Docker should output hello world after spinning up the container. Then hit enter. As you see, Docker goes ahead and downloads the image from the remote repository. That is because we don't have BusyBox 1.24 on our local box. After Docker downloads the image, it will create the container from the image and run the container. See? Docker outputs hello world, which is what we expected. Now, if we run Docker images command again, as you see, we have one image, which is the one we just downloaded, BusyBox 1.24, and the image has a unique ID. When we run the container again, Docker will use local copy of the image to create and run the container. Let's see it in action. Notice how faster the execution is. It prints out hello world right away. This is because we already have the BusyBox 1.24 image in our local box. So Docker just creates the container from the local image right away, without the need to download the image from remote registry. Let's see another example. Let's say we want to display all the contents in the root directory of the container. Just do docker run BusyBox 1.24, then ls command /. There you go! Docker outputs all the contents under the root directory of container. We can also run container in an interactive mode so that we can go inside the container. We need another two options, -i and -t. The -i flag will start an interactive container. The -t flag will create a please-do tty that attaches standard input and output. Let's see this in action. Here we do docker run -i-d. We'll keep using BusyBox 1.24 again as the image. Now we hit enter. There you go. It gets me right inside the container. We can run ls command. See? It gives us all the contents in root level. Let's say we want to create a new file here called a .txt. After that, we do ls again. We can see the file is created. Now, we can type exit to exit the container. Note that once we exit the container, Docker also shuts down the container. If I run the same container using the exact same container run command, Docker will spin up a container. But this time, Docker starts a brand new container. So if I go check out the file I created previously by running ls command, you can see it is not there. As you see, when we run docker run command, it spins up a new container. The container we created previously with a text file has been shut down. Hello, and welcome back. In this lecture, we're going to deep dive into Docker containers. We'll learn how to run containers in detached mode, how to specify Docker container name, and how to use Docker PS and Docker inspect commands. In the previous lecture, we have seen how to run containers in the foreground. But in most cases, containers are actually running in the background. We can start a Docker container in detached mode with a -d option, so the container starts up and runs in background. That means we can start up the container and could use the console after startup for other commands. Let's see this in action. We'll keep using our BusyBox image. In order to keep the container running at the background, we can run the Linux sleep command to suspend execution for a while. Let's do docker run -d busybox 1.24 sleep 1000. Then hit enter. See? Docker returns us the long container ID. Now the Docker container should be running at the background. But how can we verify that? We can find out all the running Docker containers in our local box by using docker ps command. See? The container we just started up is currently running. As you see, the docker ps command displays some container information such as container ID, image name, and the command we run. The container ID displayed here is the short container ID, which is the prefix of the long container ID. What if we want to display all the containers in the local box, including ones which have stopped? We can add the -a option at the end of the docker ps command. See? Docker also shows all the containers that I have previously run. If we do not intend to keep the container, we can add rm option in the end, so the Docker would automatically remove the container when the container exits. Here we do docker run --rm busybox 1.24. Let's sleep for 1 second, then hit enter. The container runs for 1 second, then exits. Here we run docker ps-a to list all the containers. As you see, we don't see the sleep1 Docker container we just run because it has been removed by Docker as soon as it existed. Here is another useful option. We can also specify the name of the Docker container we want to run. Here we type docker run --name hello world busybox 1.24. Now, let's run docker ps-a to list all the containers. As you see, the new container is named as hello world. If we don't specify the container name, Docker will automatically generate a container name when we run docker run command. As you can see here, we get some funny name here, such as Boring Rosaline, Matt Lemire, and Kick-Ass Hopper. Before we finish this lecture, let me show you another handy Docker command. Docker inspect. Docker inspect will display low-level information on a container or image. Let's see this in action. Let's start up a new container in the detached mode. Docker returns us the container ID. Then let's run container inspect. Copy and paste the container ID and hit enter. See? Docker inspect renders the results in a JSON array. It displays the IP address and MAC address of this container. Let's scroll up. As you see, Docker inspect also outputs some useful low-level information, such as the image ID and log path. I hope you've enjoyed this lecture. I'll see you later. In this lecture, we'll talk about Docker port mapping and Docker log command. We'll be using a new Docker image, the Tomcat image. Tomcat is an open source web server that executes Java servlets. Let's check it out. Here, we're at the Docker Hub page. We search Tomcat and enter the official Tomcat image page. Let's scroll down. As you see, Tomcat page by default runs on port 8080. We can expose a port inside the container and map the port to another port on the host by -p option. In this way, the Tomcat web server can be accessed by using the host URL and the mapped port. If you're running Docker on Linux, the host here refers to localhost. If you're running Docker on Windows or Mac with Docker machine, the host here refers to the Linux virtual machine running Docker. The format for -p option is -p host port, container port. Let's see this in action. Here, we open up the Docker Quick Start terminal. Just make the font size larger as before. Let's do Docker run -it -p8888 column 8080 to expose the container port 8080 to host port 8888. Then Tomcat 80 and hit enter. Tomcat image is about 300 megabyte large, so it takes quite a while to download. It is recommended to run this Docker command when you have good internet connection. I'll fast forward the video until the download is done. Now the image is downloaded and the container is up running. We can access Tomcat server through web browser. First, we'll scroll up to find out Docker machine IP. Just copy it.
If you're running Docker on Linux, or you're running Docker for Mac or Docker for Windows, the host IP is just localhost.
Then we open our browser, paste the host IP, and go to port number 8888. See, we have opened the Tomcat console page. In most cases, especially in production, we would run containers in the background. Previously, we have learned -d will allow us to run containers in detached mode. Let's try it out here. Then we check the container status by running docker ps-a. As you see, our previous Tomcat container has existed. Let's go back our previous container run command and add -d option. Hit enter. See, Docker returns us the long container ID, and the container should be running at the background. We can check out the logs of running container by docker logs command. Just type docker log and the container ID. Oops, it should be docker logs, not docker log. Let's redo it again. See? We're seeing the container logs.